Hey guys, it's Felix. In this tutorial, we're going to implement pulse width modulation on the FPGA. But in order to build hardware that can do pulse width modulation, or PWM, we have to first understand a little bit more about how it works exactly. I have some diagrams here that should be helpful. So there are three main parts to a PWM signal. The first part is a counter. This counter is going to go up in a square wave sort of thing, or a saw wave, sorry. So it's going to start at 0, and then every time the clock ticks, it's going to go up 1. So 0, tick, 1, tick, 2, tick, 3, tick, 4, until it hits the max value, and then it's going to overflow, and it's going to turn into all zeros again. And it's going to keep ticking and generate a saw wave. Alright? Then we have a compare that's just a number that's fixed. And what we're going to do is check the counter versus compare, and if the counter is greater than compare, then we're going to turn on the PWM signal. And then whenever the counter is less than compare, the PWM signal is going to stay low. Now, if we move the compare line down so that it's closer to the base of counter, you'll see that more of counter is greater than compare, and so therefore the PWM signal, these pulses, are wider and they're closer together. And the further up compare is, the narrower these pulses will be and the further spaced out. This counter and compare obviously have to be the same number of bits wide then. So if you got 3 bits on the counter, you're counting up like this, then compare might be 101, but it has to also be 3 bits, so you can make that comparison. And then, of course, your like a single saw blade is going to be 2 to the n, where n is the number of bits in the counter. Alright, well, let's get over into Mojo. Put this thing beside it so we can see it as we go. Let's create a new project. Call it PWM. And we want to use Verilog, and the base project is fine. We'll hop on down into the source and pull up the main file here. And we're going to need to add a module to handle our PWM. We'll call it PWM. We want this to be Verilog. Alright, first things first, let's define our input and output pins. We're going to want an input for this compare value. Input, and that's going to be a number of bits wide. It's going to be n bits wide. So let's create a variable. We'll call it counter length. Subtract 1 because it's going to include 0. So if our counter length is 4, we have a 4-bit wide compare line, then this is going to be the indices from 0 to 3. 0, 1, 2, 3. So that's 4 bits. Compare. Put a comma. Alright, and then the output we'll just call PWM. That's going to be this line right here. Now, we're going to need 2 lines here, 2 values that are going to be able to store values in them. So we're going to use registers for those. First one, register. We'll do PWM. And there's 2 parts to this. We need the data, the D, where we assign a value to it, and then we need the Q part, where the value actually gets saved. And then we need the register for counter. And again, that's going to be counter length minus 1. So that's going to be the same number of bits as compare. Counter. But again, with this, we're actually going to need a data and a Q. So we'll just name it CTRD and CTRQ. Again, this is the value that we want to store into it, and then this is actually where the value is saved and stored in the circuit. Now we've used these variables, counter length, here and here, but we haven't actually defined it yet. So let's go up here, and these are going to be variables that we can assign values. We can pass values in to this module when we instantiate it, when we actually build one of these things that we're describing. So to let it know which variables to ask for when we create one of these PWMs, we're going to put the hash sign and then inside parentheses CTR length equals 8. And we're going to prefix this with parameter. Like this. Alright. So now we have the compare number coming in here as an input. We have a counter right here that we can store values in, and we have a PWM signal that we can also store values in. So now we're going to come down to the combinational logic. Get rid of that default thing. Actually, before we start this, let's hop back up. We want to wire the output PWM to the stored value of this register here, PWMQ. So we say assign PWM equals PWMQ. Now, whatever value this register PWMQ has is going to be wired straight to the output. in the combinational logic, we need to make the counter actually increase every time the clock ticks. So with this @ sign, and then right here after the @ is a condition. If we leave it as an asterisk like this, anything that goes inside this block is just going to be wired up and always run. Always, under every condition, do the things in here. In here, we're going to make the counter increase every time the clock ticks. So CTR D, this is the value that we're going to put into, that we're going to store later, equals CTR Q, the value that it currently is saved at, plus 1. So that takes care of our clock, increasing every clock cycle now. The counter is going to go up. It's going to increase by 1 every clock cycle. Now, for the PWM signal, every time that counter is greater than compare, we want to set PWM signal high. So if compare is greater than counter, whoops, it's CTR Q, that's the stored value in counter right now, then we're going to set PWM D to a single digit binary type 1. When compare, or when counter is greater than compare, PWM should be a logical 1. So here we go. And then if that's not the case, PWMD should be a logical 0. Alright, and that is it for everything that has to run continuously. Now let's move down to the sequential logic. We'll get rid of these. So this means every time the clock hits a positive edge, aka right here, that's a positive edge, not that, right here, positive edge. Every time the clock hits a positive edge like that, it is going to run, or the things in here will apply at a positive edge. If the board has been reset, then this stuff will apply. If that's the case, we want to just set the counter at 0. Counter Q is going to get assigned however many bits wide the counter is. All zeros. Okay, if it hasn't been reset, then we want to store the temporary value for the counter in and actually save it. Counter Q is going to get counter D's value. And then finally, we want to save the PWM value and store it. So PWM Q is going to get PWMD value. Great, so that's saved. Now we're going to head over to the main file and create an instance of our PWM module. This line let's go ahead and just change this to only be the first 7 LEDs. LED 0 we're going to use on our PWM module, but we have to make sure that each of these LEDs are driven by something, so we're just going to turn them all off by hooking a logical 0 up to them. And now we'll instantiate our PWM module. So how we do that is the name of the module, and then we're going to do the same # parentheses to allow passing in the variables. So dot variable name, counter length, and then inside parentheses we're going to give it the length we want. Let's just use 3 for now, since that's what I have out here, 3 bits long for the counter. And then we're inside parentheses here with a semicolon at the end. We're going to connect the inputs and the outputs to things in the main circuit. But before we do that, we need to give the PWM module that we're instantiating a name. We could also just name it PWM or PWM instance. And now, to connect all of the inputs and outputs, first we have clock and reset. So we are just going to give it the clock that's right here. Next, the reset variable is going to be this reset, which is inverting the default reset button. It's normally active low, but this line, when we invert it, it makes it active high. And we want the active high reset, so we'll put that in. This is the variable that you're passing in to the PWM module. This is this. This right here comes from here. So the thing right after the dot is from the module. That's the name in the module of the input or output. And then inside the parentheses is the value that you're giving the module from here. Next we have the compare. And we want to give that some value, one of the possible values. So since it's 3 bits long, let's set it at 110 at 6. So 3 bits of binary 110. And our output we called PWM, and we want to hook up LED 0 and drive LED 0 with that signal. Alright, let's save that and build it. Okay, finished building, we'll upload it. Okay, it's finished, and we can see that LEDs 1 through 7 are off, but LED 0 is on, and it may be a bit hard to see from this camera, but it's not on at the same brightness that the done LED is on. So it is actually pulsing. Now let's add different pulse widths to the other 7 LEDs. What we could do is just copy this and paste it a bunch of times and just modify the compare value and the LED value, or the LED number for each of these, and give them all different names. But I don't really want to do that 7 times, to be honest. So what we can do instead is put this inside a generate loop, a generate for loop. So we're going to have something called a generate variable, and it's going to use this variable to help in giving each of these instances unique names, because in the loop they're all going to have the same PWM instance name. So generate keyword, and we're going to end generate. And then we're going to have a for loop. So we're going to start with I equals 0, and we want to go as long as I is less than 8. So we're going to have 0, 1, 2, 3, 4, 5, 6, 7, and 7 will be the last value of I that's in this loop, which is great because 0 through 7 are the indices of our LED. And then we want I, at the end of every loop cycle, we want I to equal what it was plus 1. We'll just increase it by 1 every time. Alright. And put an end. And then we're going to have a colon, and right here is going to be where the generate loop combines this genvar with a name in order to figure out how to identify each one of these things. So here we can, let's just call this PWM thing. And then now, instead of hard coding in values for these, let's use this I variable that's going to range from 0 to 7. So first we want to get the LED that corresponds. So we'll first get LED 1, and then as it loops through all of these, we'll end up activating all 8 LEDs. And we want the compare value to also correspond to the brightness level. So it's either going to be 0, 1, 2, 3, 4, 5, 6, or 7. So all 8 values are going to correspond with the 8 different LEDs. Go ahead and save that. And build it. And it's giving us an error and I think I know what we did wrong, but let's just check it. Okay, error. Signal LED 7 is connected to multiple drivers, and it appears that LEDs 1 through 7 have been connected multiple times. Well, that actually makes sense because we just connected all of them down here, but we already wired LEDs 1 through 7 straight to logical 0 up here. So at this point we can delete that line and build. Alright, finished building. Let's upload this. Perfect. We can see we start with LED 0 and it's pretty much totally off. And then as we move down, they get brighter and brighter and brighter. Now, why is that? Let's look back over here at our model. The things that we're changing for each instance here, we've got 8 of the instances, and I is ranging from 0 to 7. So we're wiring up LED 0 with compare value of 0. If we check that over here, imagine this compare line being straight down here at the bottom. How much of the counter is going to be greater than 0? Well, the whole thing. So this, the signal is pretty much always going to be high. And so that makes your LED 0 be the brightest. Okay, what about the last one? The last LED would be LED 7, compare value 7. And since our thing only counts up to 7, imagine this thing being all the way at the top. How much of the counter is greater than compare at 7? Well, pretty much none of it. So the signal is going to be practically low the entire time. And that's why that last LED looks like it's totally off. It's technically blinking just a hair right here at the tips of these, but it's on for such a short amount of time that it just appears to be off. I hope this tutorial has helped improve your understanding of what exactly pulse width modulation is and how it works on a very low level at hardware. And if this has been helpful, please like and subscribe. Thank you.